As you know very well, job shop scheduling is a technology that can be used in several fields. For example, for moving, we were using in our lab for moving containers in a terminal, or moving packages in a production environment, or moving aircraft in a terminal moving area, or like today, moving trains in a railway network, or moving packets in a computer network, or even moving persons in a busy pedestrian area, and so on. So today I just give you an application of job shop scheduling with a way of representing it, that is a special graph. We basically, one professor in our group invented this graph 20 years ago. So this kind of webinar is also to celebrate the 20 years of the alternative graph model for job shop scheduling. And I focus on the railway application because we have a strong background on this topic and a long history of publications and collaborations with industry. So, who is the speaker? I am an associate professor in operations research. I work at Roma Tre University in the Department of Engineering. As you see here, Dipartimento di Eccellenza means one of the few excellence departments. We have a stamp for the Ministry of Education, and we also have funding for this reason, being an excellence department. In this department, I teach operations research and applications in different fields. And the background of knowledge in this particular field of research is a combination of different knowledge: OR, computer science, railway engineering, and also intelligent transportation systems. So we use this background to develop new techniques that are useful for industry, for railway industry. Okay, here you can see some more information about myself. Just want to tell you that we have not just some in academy some recognitions, but we also have a strong track of collaboration with industry. Industry mainly in Europe, so Italy, Switzerland, UK, Netherlands, France, just to say some collaborations. I'm also coordinating in Italy a chapter of the Italian Association of Operations Research that is dealing with public transport optimization. So I also apply my knowledge to other means of public transport. Today we will start with an overview on this alternative graph method with a high level overview. Okay, this is not a presentation just for OR people or scheduling experts, but the idea is to have a presentation that try to reach the interest of a larger group of people, okay, a larger audience. For this reason, I won't be too technical. I won't be too detailed on some techniques or some parts. But of course, if you want, I can I can go more in depth at the end of the presentation. What is an alternative graph? Again, it's a way of formulating a job shop scheduling problem. What is a job shop scheduling problem? Just for people that are not familiar, is a scheduling problem, one of the most complex, in which each job corresponds to a vehicle or a person taking some actions. Each job is composed by a set of operations, or these are the most atomic items, the most atomic actions to perform by this job. And then the set of operations are predefined. They are to be executed in a row. Sometimes can also be flexible, so you can change the order of processing the operations in a job. Each operation is an action that is related to a job and to a resource. And the resource in this context has a capacity. And each resource can be shared by different jobs. To have a more close loop to what a job shop scheduling solution is, here I give you a Gantt chart in which you see vertically, you see with different colors the jobs, and horizontally, you see the resources. it's easy to see that the time is going from left to right and the resources are shared by different jobs. Okay. You need to find a solution that optimizes this assigning jobs to resources. Then why job shop scheduling is so interesting for railway? Because it's easy to represent a train scheduling problem as a job shop scheduling problem. Each job corresponds to a train. Each resource corresponds to a piece of track, a piece of infrastructure. Each operation is the use of a piece of track by a train. A train is occupying or is reserving a piece of track. And when you look at the job is a set of operations. So basically, it's a train routes. Okay, it's a possible routes for a train. Why alternative graph for representing this particular job shop scheduling problem? We will see. Basically, the alternative graph helps you to model some special constraints of the problem. In general, in the alternative graph, each node is an operation. Each arc is a constraint. So it's very simple. If you have many constraints, each constraint is a graph. If you have a set of operations, each operation corresponds to a node. Then here I mention a particular type of constraint that is very important because the alternative graph is working very well with this special constraint. And the constraint in the scheduling terminology is called blocking constraint or no start constraint. This simply means that each piece of track can only be occupied by one train at each time. Okay, so each piece of track can be empty or can be occupied by maximum one train. This type of constraint is a so-called block and store, and the alternative graph is very suitable to represent this type of constraint. Here you see an example in which you see two trains that want to occupy this gray piece of track, and one of the two will go with a green, this one, the other one will face a red. So at the end, this resource will be first occupied by the violet train, the second one here, and then the blue one will go after. This can be represented by a specific arc that gives the precedence of the violet to the blue. Okay, and you can represent a blocking constraint through this arc. Then we can and need to represent other constraints for this problem. And in general, each train has a kind of time window to perform its operations. For example, it's traveling in a piece of track. There is a time window to use this piece of track. How can we represent time window? We can represent them as minimum, maximum time to start the operation that correspond to the train on that piece of track. So we need to fix a minimum time to start the operation and a maximum time to start the operation. This can be easily done to some special arcs in the graph. We call this, according to the scheduling theory, we call these arcs release when you want to fix a minimum time. For example, here you have node I and the release arc is node 0i. Or you can fix a due date if you want to fix a maximum time to start an operation. That is the arc IN. If you represent it as a due date, it's not mandatory. You would like to satisfy that constraint, but it's not a must constraint. If you want a must constraint, if you want the maximum time is really rigid, fixed, then you use a deadline. And the deadline is in the graph representation simply another type of arc, I0. So with these three types of arc, you can represent the time window for traveling in a piece of track by each train. This is very useful, we'll see, for different applications, from timetabling to rescheduling applications. Then there are many other types of constraints. I don't want to list all of them, but you can imagine that you need to connect services. For example, there are passengers that want to move from one train to another train in a station, change train, and then we will need a service connection. Or we might need a rolling stock connection. That means the same train performing two different types of services. Or we might need constraints regarding the timetable, for example, the arrival departure time from a station. Or we might need constraints on the resource availability. Maybe a resource is not only available for traffic, because there might be, for example, some maintenance of that resource, and then you fix the availability time window for that resource through special constraints. Or you might need to manage, to optimize the travel time of trains, and maybe fix a minimum maximum travel time of trains. So you can continue in this way and formulate through these arcs in the graph several different types of constraints. What are the modeling assumptions? Just till now, I give you the feature of things that you can model, but we also need to fix the limits of the model and what you can do, what you can optimize, what not. For each operation, you have a start time. That is the first type of variable I introduce. This is clearly a timing variable. And you need to find the best time to start each operation. Okay, so this is, let's say, the most microscopic variable, the time. And then you have a duration time to perform each operation. The duration time in our today presentation and in most of our research is a fixed duration, is an input data. Now, recently there is a stream of research that is dealing with stochastic duration times, but I will not discuss too much today. So today, the duration time will be a fixed value. That is also called processing time of the operation. Then another type of variable is the train sequencing. You need to decide partially or totally, depends on how much flexibility you have in optimizing the traffic flow, the sequence between the trains. So if two or more trains are sharing the same resource, you need to find the sequence. This can be represented very easily in the model through a special set of arcs that are called alternative arcs, that also give the name to the graph. The alternative arcs are dealing with the sequencing decisions. As you see here, you have two trains that have to enter the same piece of track, and this piece of track can be only occupied by one train. You need to decide which train goes first. If B goes first, then you will introduce one special type of alternative arc. Otherwise, if A goes first, you will introduce another type of alternative arc. So basically, every time you have two trains, you have two alternative arcs, and you can select only one of the two, because you need to decide AB or BA. Here you see the representation as alternative graph of the problem. So the dotted arcs are the alternative arcs. So if I decide that B goes first, then means I will let the B go to the resource, process the resource, then I will clear the resource, and then through this arc, going from H to I will allow A to enter. If I want A first, I will do the opposite. First A process the resource, then clear the resource, and then give the room for using it to B. So this pair of arcs is called a pair of alternative arcs and represents the train sequencing variables, decisions also. Then we also have another additional level of variables, the routing variables. As I told you, the routing of each train, so the set of resources used by the train, can be either fixed or flexible, or partially flexible. Usually it's partially flexible. You can only change some parts of the route. It depends, depending on this level of flexibility, we give a name or another name to the routing problem. Okay, imagine you have a route in the timetable for each train, so kind of default route. You can locally change the route or globally change the route. The difference between global and local, you can think about local like a small change of routes, few resources are different. Between two routes. Global routing, several resources are different. As you can see here, the blue, the train is going from left to right. Below, the train can go still to left to right, but change the route. Okay, if you change the route in a station, usually this is a local routing. If you change the routes in several stations, then it's a more global routing. So we remember these three types of variable: timing, sequencing, and routing. Then fixing the timing variables, you can also clearly decide the arrival and departure time, because if you fix timing of in each operation, then you will also fix the time to arrive at the station and the time to leave at the station for each train. And this timing can be also flexible. And then you might have also some flexibility when you fix the so-called running time of trains, that is the travel time in a piece of track. And also the dwell time can be flexible. That is the time that the train is waiting at a station to allow passenger enter the train or leave the train. You can also think about having a time window with a minimum maximum values for the running time and for the dwell times. And then in general, I want to remark that the assumptions on the time and resource granularity are very important. The more you go in deep in representing the timing, like at the order of seconds, milliseconds, even, the more you will have an increase in number of variables. The more you divide your track in small pieces, like you can divide the track in block sessions between signals, or you can divide the track in track circuits, the distance between two track circuits, and so on. The more you go in deep, the more you have a macroscopic model, the more you will have complexity then to solve the problem. The level of granularity depends on the customer objectives and the customer business rules, the constraints. So it depends on the level of optimization. If you are in a time tabling, planning, or if you are in a real-time context, there might be a very different type of granularity in representing traffic flows and infrastructure. So problem complexity is basically connected to granularity. As it has been demonstrated by Machis and Pacciarelli, that are the two inventing this alternative graph model, that a problem with a few trains, already with 3 trains and blocking constraints, it's already an NP-hard problem. So finding a feasible solution might be NP-hard. This means that we are dealing with a problem in which the complexity explodes exponentially with the number of variables, and especially with the number of sequencing and routing variables. The timing variables are slightly easier to solve, especially if you represent them through shortest path problems. But okay, in general, the message here is that problem complexity strongly depends on granularity. To give you an idea of what is the complexity when you are sequencing trains, I put to you an example of graph, alternative graph. Here you see 2 dotted arcs that form a dotted pair, and you want to select one arc among those two to have a so-called complete selection of the arcs. Let's try to select the arc 6, 2. If you look what happens inside the graph, it happens that there is a positive length cycle in the graph. And as you know, when you represent a problem with a graph, if there is a positive length cycle, the solution is infeasible. So in theory, we cannot select this arc. We should select this other arc. But if we select this other arc, we have the same problem. Again, a positive length cycle. When we reach this status in the graph, this means that there is no feasible solution. This means that some other constraints that have been fixed before are infeasible. We can also understand which one might be infeasible, because it might be involved with the arcs that are involved in the two cycles. So the alternative graph can also be used to detect infeasibilities. That is very important, because if you detect the constraints that are infeasible, imagine you are in a planning phase, then you might correct those constraints and recover feasibility. Then, of course, it's important not just finding a feasible solution, but we want to optimize the performance indicator. The performance indicator that is easier, I want to say, to optimize is the one related to the timing of the operations. Why? Because we can use powerful scheduling theory techniques. And we can transform the problem of, for example, minimizing delays or minimizing completion time in a make-span like problem. So minimization on the make-span. So minimization on the longest path in the graph. As you can see here, the alternative graph for this problem was optimized by minimizing the makespan. And this is a solution where you have longest path. And this solution, the length of this path, is exactly the maximum completion time or the maximum delay that is in the graph. So there is a correspondence, very clear correspondence between the timing decisions and if you want to minimize the maximum completion time, for example, and the makespan-like objective function. So you can use all the knowledge in the scheduling theory if you have a timing objective function. Okay, objective function depending on timing variables. The problems get more complex if you change the objective function. Okay, so if you have objective function different from timing, you can still represent the optimization problem as an alternative graph, but you might have more problems to solve it. Okay, and especially to solve it to near optimum. So you need to customize the algorithms, but you cannot fully use the scheduling theory that is behind that theory, that formal representation of the problem. How to optimize the performance indicators? More in general, you might have a single objective function, for example, minimizing the delays or minimizing the cost, and you can optimize it through a dedicated algorithm. But you might also be in a situation where you have multiple objectives. For example, in this paper with Corman et al., we were dealing with a bi-objective optimization in which the infrastructure manager was trying to minimizing delays. We will see then later the so-called consecutive delays that are delays due to conflicts between trains. And the train operating company was dealing with satisfying the passengers and maximizing the number of connections that are satisfied. These two objective functions might not agree. So you might find that the best solution for one objective is very pure from the other objective and so on. So here I show you that if you keep all the connections for the passenger services in the station, yeah, then you might have a very large delay. If you start dropping connection, you might reduce the delay because there is, you imagine, every time you drop a connection, the second train does not need anymore the first train. So if the first train is delayed, the second train can still leave the station. While if there is a connection, the second train needs to wait that the first train arrives, open the doors, and the passenger move to the second train. So this is also called the wait or not to wait problem. And this is a kind of bi-objective optimization problem. Then there are other types of representation of multiple objective optimization. For example, one that was used several times is a lexicographic optimization. When you have multiple indicators that are important, but one is more important than another one, then you can first find the set of optimal solution for the most important objective function. For example, minimizing train delay might be most important. And then among those solutions that are minimizing delay, you might select the one that has less energy consumption. This is called lexicographic optimization. So you have another of importance in the performance indicators. Another type of situation in which you need to handle multiple performance indicators is when you have different classes of trains. Imagine you have in your network international trains, regional trains, and freight trains. Clearly, the international train are most important, then the regional, then the freight. Then you can build up your schedule by giving first priority to the international train. So you first introduce the international train in the schedule. Then you introduce the regional, and then you introduce the freight. Here I just give you a pointer to a framework that is dealing with this type of problem. And each type of train is a class of train and is a kind of multi-class train scheduling problem. And then, of course, you also have more in general multi-objective optimization. You might need to combine multiple indicators, and you can use, for example, weight sum or epsilon constraint methods. Or you may even might be in the case in which you have multiple decision makers and you end up with a game. Recently, Professor Kommer was publishing a nice paper on transportation science where the game was the infrastructure manager and the operating company were trying to optimize certain jetting function, not necessarily in agreement with the passenger, and the passenger were optimizing their own jetting. They all have a rule in the game because the passenger can decide which train to take, and the infrastructure manager and the train operating company can offer different type of services. So here there's a kind of stackable game in which the leader is the train operating company, the infrastructure manager, the leaders, and the followers are the passenger. So the passenger can still play the role, but as followers. So you can be in a situation in which game theory is also applied. And all of these techniques to optimize multiple performance indicators have been applied through the alternative graph model of the problem. In this second part of my presentation, I will discuss the literature. I will try to give you an overview on the literature on some topic in the railway field. Okay, going from simulation to optimization topics. Okay, in which the alternative graph methodology is used. Here you have a classification of the literature, and you see that you have a recent survey, IEEE ITS journal, in which you have the number of papers that were dealing with the different types of techniques. As you can see, the alternative graph technique is the second most used. The first most used is mixed integer linear programming. Actually, there is a strong link between these two formal representation of the problem that I will explore later on in the presentation. Both of the two formal representation of the problem are resource dependent. So the problem depends on the level of granularity on setting the resource, because as you have seen before, the number of resources then have an impact on the number of operations that are in the graph. Another type of representation of the problem is more time-dependent formulation. So it's more depending on the granularity on time. For example, there are some integer programming formulation that are time-dependent. Now, I don't want to tell you which one is the best approach, but of course, the two approaches have positive and negative points depending on the level of granularity you need to use for the resources or for the time. Which solving methods exist? Okay, now I won't go too much into the details of the specific algorithms, but I want to give you an idea of which type of algorithmic framework you can develop. Okay, first off, because going to the algorithmic framework, I give you very extreme classification. One possibility is to model the problem as a MIP, as a ternary graph, or as an integer problem, and then give to a commercial solver. Now, the positive is that the commercial solver, so the mathematical formulation can be very general. You can formulate any kind of rules, business rules, constraints, objectives, and so on. What is the controls? Usually the commercial solver is a general solver, is not a customized solver. So the more the instance, so the number of operations increase, the more the problem complexity increase, the less the commercial solver is able to solve the problem. So you might end up that when you use the commercial solver, you cannot really solve real world instances. So you need to go for a smart solver. What is a smart solver? It's a problem dedicated solver that can also be incorporating the general commercial solver, but must be customized. Okay, customized why? Because we need to reach good performance, because we need to reach good scalability. And what is the problem? This would be fantastic, a smart solver, but having a smart solver sometimes is very difficult to develop and to maintain, because every time you have some new business rules, you might correct your smart solver, you might correct your algorithms in the solver. Every time you have a new jetting function, you might reconsider your algorithm. You might study again the property of the model, and you might again develop new algorithms. So there is a lot of work behind a smart solver. But the smart solver so far is the most promising approach. When we deal with alternative graph-based software, we will see this type of software is based on a mix of algorithms, depending on the type of variables. We will see heuristic algorithm, meta-heuristic algorithm, and even exact methods, depending on the type of variables. Okay, just to keep in mind, the timing are easier, then you have the sequencing, and the routing. So the routing is the most complex. So when we will deal with the routing variables, we will go with heuristics. When we will deal with the timing and sequencing variables, we might use also we might develop exact methods. Okay, and this also not only depend on the type of variables, but this also depend on the type of constraints and objectives that are involved. Then a key in both cases, general solver and smart solver, is the pre-processing phase. The processing phase is a kind of knowledge that you collect before solving the problem. This knowledge can be about the routing, for example. How can I filter the routes? Do I really need all the routes for all the trains? Can I filter? Some routes might not be useful for this case, for solving some specific problem. Or can I pre-select some variables? Can I prefix the values of some variables? Because I know that in the optimal solution, there always be that one, the values. For example, if a train is has to be sequenced with another train, but the second train is really coming much later in the future, then of course the first train the first train that arrives in the resource will go first. So sometimes you can pre-select variables, and other times you can even reduce variables. You can filter like you do with the routes. You can reduce the number of variables. The solution will be still very good or even optimal sometimes. So the pre-processing phase is a kind of phase of where you study the problem and you try to somehow simplify the problem. And this can be used both when you use the general commercial solver or when you use a smart solver. Now, the trick to solve a real world instance, the trick to solve a practical side instance is problem decomposition. The problem decomposition will give you the power to fasten the convergence of your algorithm, to improve the performance, and to improve the scalability. What type of decomposition exists in practice, and what type of decompositions exist in this particular field of research, and they were used and they were successfully used? The first one is temporal decomposition. There are a number of approaches, for example, to resolve real-time train control problems that, for example, dealing with speed control or train sequencing, routing in some cases, are based on rolling horizon or model predictive control approaches. These are approaches that have been very much used. Why? Because in real time, information is changing dynamically, quickly, and you need to update information. And this can be done in this kind of problem decomposition very easily. Another type of problem decomposition is the spatial decomposition. For example, if you need to coordinate traffic flows in a very large network, you might decompose the network in sub-networks. And then you need to deal with a coordination problem. This is also sometimes the structure of a Bender's decomposition, where you have a master, and when you are so a higher level and then a lower level in your coordination approach. For example, maybe I can mention the approach of Professor Mannino that is very powerful with the Bender's decomposition. Other types of decomposition you can find in the literature are depending on the types of variables. For example, you might decompose the problem in timing, sequencing, and routing approaches. So you solve there are these problems are of course interconnected. We will also see, if I have time, with some examples. But you can think about disconnect the problems, so fixing a different as different subproblems, timing, sequencing, and routing, and then put them together at a certain point. Okay, so you might also decompose by type of variables, not necessarily by time or space, but also by type of variables. Actually, the solver that I will introduce later is based on this type of decomposition. Sometimes you also have decomposition in layers. So you have not really a clear distinctions on the type of variables, but you have different sub-problems. You detect the original problem and you divide in sub-problems, where you might combine different types of variables, and you might introduce different layers. This is another type of decomposition that is much used. Now we'll try to discuss with you how this methodology has been applied to solve some practical world problems in Europe. These problems go from real-time traffic management to tactical timetabling to capacity consumption. Okay, so quite different types of problems, but all of them you see are dealing with the optimization of traffic flows at different level in different stage of optimization. Capacity consumption is more at planning level. Then timetabling, we move to the tactical, and then the real-time traffic management, we move to the operations. Okay, first I will discuss the real-time traffic management, because this has been the first and most also successful application so far of the alternative graph methodology. First problem that I want to discuss with you is the local train dispatching. Usually, a dispatcher is a human that has a region to control traffic flows that is quite limited. This can be a single line, or this can be a junction. This can be more in general a dispatching area, so it might also include a few stations or a part of a large station. Okay, this is called the local train dispatching. So here the problem is to optimize the decisions that have to be taken by this human locally in a small piece of the network. And of course you need to optimize this small piece and be in coordination with the neighboring local areas. Another type of problem that is still a dispatching problem is the combination of controlling trains in a local area and controlling the speed of trains. So helping the person that is guiding the train driver to find the optimal speed trajectory. So you can at the same time give advice to the driver and give advice to the human that is controlling locally the dispatching area. This type of coordination between speed control and local dispatching, including sequencing, local sequencing and routing, has been subject of a number of European projects funded by the European Commission. I mentioned here one very big problem, one big project of millions of euros that was successful in Europe some years ago. That was using a software that I developed when I was at Delft University of Technology. It is called the Roma software. That inside incorporates the alternative graph representation of the problem. And the alternative graph representation of the problem, we will see later, is managed by another software that is inside Roma software that is called AG library. AG is alternative graph. Library means a collection of algorithms to solve problems represented as alternative graphs. As you can see, the architecture of this solver is from one side you optimize traffic flows, from the other side, or in parallel and then coordinated, you find the train speed trajectory, and you coordinate the train speed trajectory. Basically, this is exactly the coordination between train speed trajectory optimization and traffic flow optimization as sequencing and routing problem. So as you can see, this was solved as these two sub-problems solved in an iterative way. Okay, and this was having an interaction also, of course, with the human and with and giving information to the field. This was still a project in a laboratory environment, but they were using real-world data from different infrastructure managers and train operating company in Europe. And was everything was simulated through in a simulation environment. So there was a simulator and there was an optimizer. And this where the optimizer was taking decision and giving this decision to the simulator. And they were testing not just the software Roma, but they were also testing another software called Recife that is developed by a research group in the north of France, Lille. Okay. Then another type of problem in real-time traffic management that is important to handle is the global train dispatching. The global train dispatching, we are enlarging the scope. Now we need to coordinate several local train dispatching areas. This problem is getting more complex because the number of variables increase, the size of the network increase. And for solving this problem, you need to have a number of decision support tools, one for each dispatcher, that we call dispatcher graphs. Each of these graphs is an alternative graph. And then from the other side, you also need to have a representation of the coordination problem. You need to take decisions to coordinate the different dispatchers in the different areas. And this has been done through two graphs. One is called border graph and one is called the coordinator graph. The coordinator graph is another type of alternative graph. So alternative graph is used both for the dispatcher and the coordinator. And these two boxes, one at the higher level coordination, the second one at lower level, several dispatchers, were exchanging information on the specific graphs. Okay, I don't want to go into the detail of the exchange of information. I just mentioned that the information that was shared was dealing with time windows to perform operations by the coordinator, and by the dispatcher the longest path that they found in each specific graph, giving information on the special solution found by the local dispatcher in each area. This was the global train dispatching was something that I did in collaboration with Professor Common during his PhD thesis. Then we were talking about this local train dispatching, train speed control, global train dispatching. The real-time traffic management is also dealing with disturbances. And different types of disturbances requires different types of decision support. If you have a small delay, for example, one single train delayed, or for example, a few trains delayed with a small delay, then this might be called like light disturbances. And the rescheduling task is mainly to change the timing of the operations and sometimes change the ordering. When you have a larger disturbance, for example, multiple delayed trains, or even some trains that is disrupted, that is blocked in some track, or some track that is no more available, then you end up with a much more serious disturbance. When you have a very large disturbance, you have very often the need to recover from infeasibility. So in this case, you might use the alternative graph basically to detect infeasibilities and to relax some business rules. For example, canceling some services or rerouting globally some services. So depending on the type of disturbances, you have different types of formulation, but also different types of use of the tool. Then the use of the tool depends also on the type of network. If you want to take a decision at a planning level on the entire, for example, when I was in the Netherlands, on the entire country, then you might need a very macroscopic representation of the problem, high level representation of the problem, and then you might take some high level decision. If you go to the more in deep and you, for example, want to control the speed of the trains, then you really need to divide the piece of track circuits and go into really the detail of seconds, milliseconds. So the type of network representation is very important. And also recently, passengers start playing a role. There is a recent stream of research in which in the alternative graph we're using not only the train traffic flows, but also the passengers traffic flows. So you can imagine different layers of flows on the same graph. And this combination of passenger flows and train flows allow you, for example, to optimize new performance indicators. Then you can optimize the travel time of passengers. Now you can optimize decisions that are directly involving the passengers. For example, which train to take by each passenger, or for example, the train occupation, and so on. So this additional level of detail, of course, has a strong impact on the granularity, has a strong impact on the complexity of the problem, but also open new opportunities for optimization. Okay, now I move to the tactical train timetabling. Tactical train timetabling is no more real time, is planning, but is not strategic planning. Is a planning that is very close to operations. This can be done one day before, some days before, a week before. And when you do this planning, you know a lot of information. Even in some cases, you already have an existing train timetable. And you, for example, might want to modify some services in the timetable or add some services in the timetable. When I was collaborating with the Swiss Railways, they already have an existing timetable. What they wanted, what they are also still searching for, is the best way to insert a new freight train. You might imagine that Switzerland is in the heart of Europe, and a lot of countries want to cross Switzerland. A lot of freight companies would like to cross Switzerland with their freight trains. But if you accept a new freight train, this might have an impact on the passenger trains. So their objective was to reduce at the maximum the impact on the passenger trains, but at the same time allowing a new freight train. From the point of view of the return on the investment, you can easily count. I mean, if you have a new freight train in your timetable, you have a gain of millions of euros, especially if this has no impact on the passenger flows. So this is a very interesting problem, inserting new services, and this is an example of tactical train timetabling. Okay. Other examples of tactical train timetabling, you might have more flexibility. Sometimes you might not have really a timetable. Sometimes, for example, when I was collaborating with the Dutch Railways, they have an existing timetable, but this existing timetable at the tactical level was not conflict-free. They still have some conflicts in the timetable. But this timetable was the result of an agreement, a discussion and an agreement with the train operating company. In the Netherlands, you have one train operating company that has more than 90% of passenger trains. So if you find an agreement with this company, basically you almost have a feasible timetable. So you were taking this non-conflict free timetable, but satisfying the business rules of the train operating company, and they were asking me and asking the research group to adjust the timetable to get a feasible one. So perform minor changes to find a timetable conflict-free. So a timetable in which there are basically no red signals for the trains. So the trains can run in a dedicated time and space path with no conflicts. Another type of situation in which you might need to use the tactical timetabling is to define and design at tactical level emergency timetables. The emergency timetables are timetables to deal with emergency situations. I remember the first time I was collaborating on this topic with Dutch Railways, they asked me to look at the book of emergency timetables. They basically have for each emergency scenario in which you have a serious capacity reduction, cancellation, and the problem in the infrastructure and so on. For each situation, they were having a strategy. So you can imagine how big was this book and how difficult was this book to be applied in practice. So the idea was to develop a strategy to automatically or semi-automatically give us support to deal with emergency situation. Okay. This is a special type of train timetabling because in this case you might deal with, as I told you before, with infeasibilities. So you might need to removing some services. Typical actions are canceling services nearby the area where there is a disruption, so a track that is blocked, or changing the routing of some trains, either locally or globally. Okay, here you see two situations: one in which you cancel several trains, one, and another one in which, and here you have the disruption. And in the same disruption, here you don't cancel trains, you keep some of them, but you see that the waiting time is very long. So here you need to understand, what do I do? I have a very long waiting. Here you can recognize the waiting. Here is time, sorry, and here is space. Okay. So when you see a block that is covering a big amount of time, it means that a train is going very slowly or is even waiting here. So the more you have the train in a disrupted area, the more you might have situations like that. The less you have trains in this area, of course, the less waiting, but also less trains are running. So you need to find a trade-off between these different types of actions: long waiting, cancelling, or global rerouting. So tactical timetabling is also used to define so-called robust timetables. There is a very significant amount of literature that is dealing with timetable robustness. The robustness is not really cannot be defined in a unique way. Different researchers have different definitions of the robustness. For example, if I think about Fischetti was introducing light robustness concepts, other researchers were introducing other types of robustness concepts. The robustness in this discussion and in the alternative graph use of this concept is a kind of assessment of how much of the ability to recover from disturbances. So you have a timetable, you have disturbances, you want to see if you can adjust this timetable to fully recover disturbances. Okay, recover disturbances is not just reducing delays, but it can also be considered when the delay completely disappears. Okay. This is done, for example, by some researcher in my group by developing a coupling between a scheduler that is optimizing traffic flows and a traffic simulator that is a stochastic simulation that is also generating disturbances. So the simulator generates disturbances. The scheduler finds the most suitable actions to recover such disturbances, and they exchange information. Okay. So by this round of exchange of information between optimizer and simulator, then we assess the robustness of the timetable. Other line of research in tactical timetabling are dealing with finding the best selections of routes. One of my PhD students is working on exactly this problem. The question is, do I really need all the routes, or can I filter the routes and have less routes but the good ones than to give to the real-time traffic control? So at this stage, we are trying to understand what routes are most useful. This can be in general, or this can be depending on the specific disturbance or disruption situation. This is a very complex problem because you need not just to look at the routes, but you need also to look at the impact that each route has on the timetable, so on the schedule that you compute. And you not just need to find one route, but you need to find a set of routes for each train, and eventually also the order of importance such routes. Then you have other problems. Here I just discussed with one item, but it's a very big word. The integration between train timetabling and other strongly connected problems. For example, I did a lot of research in computing optimal train timetables integrated with optimal maintenance scheduling. I was dealing both with rolling stock maintenance in some cases. For example, when I was collaborating with Trenitalia, the train operating company, one train operating company of high-speed trains and local trains in Italy, and also maintenance scheduling in terms of infrastructure maintenance scheduling. For the infrastructure maintenance scheduling, I can refer you to some competitions that were proposed by infrastructure managers at Inform's railway application section. This section of Informs is dealing with enhancing the collaboration between railway managers and OR people. And for 2 times, the competition was dealing with the best, how to find the best integration between train timetabling and maintenance scheduling. Other type of integration can be dealing with rolling stock circulation and timetabling, or can be dealing with personnel scheduling and timetabling, so crew scheduling and timetabling. So there are different problems that somehow interrelated with the train timetabling, and that should be solved in an integrated way with train timetabling. About this item, the alternative graph is one possibility, but there might be other tools that are also, of course, very useful or more useful to deal with the integration. Okay, now I can move to the assessment of capacity consumption. That is another field of research that I want to mention. In general, this field of research, the alternative graph, was used as a simulator. For example, I mentioned the collaboration that we had with the Dutch government, the government in the Netherlands. Some years ago, they were dealing with a highly political problem, the problem of deciding how much to invest in the renewal of the railway infrastructure to improve the capacity, to improve the safety, to have a more modern technology to run and control the trains. In this context, they asked our Delft University of Technology and our research group at that time when I was in Delft, to assess different types of signaling system and positioning of the signaling system, and do this through simulation. So we were using the alternative graph as a simulator. Of course, you can use as a simulator that is also intelligent, because also use optimization inside. And we were dealing with the simulation of normal traffic flows or disrupted or slightly disturbed traffic flows. And all of this to assess the capacity, the capacity consumption. And we developed a so-called concept of dynamic infrastructure occupation. That dynamic means assessing the infrastructure occupation not in an ideal stage, like the UEC concept, that is represented here through the blocking time theory developed by Pakol and Professor Hansen. Here you see a blocking time diagram. But dynamic. So dynamic means that we were dealing with the infrastructure occupation in case of stochastic delays, in case of different types of response and of the signaling system and automatic train protection system, different type of signaling system, different types of ERTMS level from level 1 to level 2 at the time, and the different configurations and position of the signals. And also, this is special from alternative graph, that we can also deal with the different traffic control actions, because we can not just simulate traffic flows, but we can also reorder trains, rerouting trains. The combination of all these aspects was defining the so-called dynamic infrastructure occupation. All of this was used to find to simulate a lot of scenarios and trying to suggest the best investment on the type of signaling system and on the positioning of the signaling system in the Dutch railway infrastructure. Other types of assessment of capacity consumption can also be done when you build new railway lines. For example, I remember one of my first discussion with the Dutch infrastructure manager was to find the best way to move traffic flows, freight traffic flows, in a new freight line. That is called Beuterroute line. This is a line that is crossing the passenger line. So we need to find not only just the best speed of the freight trains, but also find the time window to dedicate to the freight train. And this was a problem of traffic flow optimization, but it was also a problem of capacity consumption optimization. And then, of course, when changing the resources availability more in general, this might have an impact on the assessment of the capacity consumption studies. Okay, now the fourth part of my presentation is dealing with a slightly more detailed description of one application of the alternative graph methodology. I selected as application a train rescheduling application. And for this application, I will discuss more in depth how to define the mathematical model, and will also give some room to describe high-level scheduling routing algorithms, at least the idea behind those algorithms. And then I will also introduce some practical test case, okay, dealing with the special railway business rules and objectives. As a practical test case, I will mention our collaboration with the Alstom group in Italy, Alstom Ferroviaria Bologna. And as customer, we had at that time the UK railway, Network Rail. Okay. I have time to discuss this application. If you don't have question, I continue. I continue starting from a little bit scratch. I want to go slowly to the point here. I start with explaining basically what is train rescheduling. A train rescheduling is a problem that you face after you have a timetable. As you can see here, it's a simple line where there are some stations and trains. The red train goes from bottom to top, the blue one from top to bottom. They meet, and the meet and pass can only be done at the station. So one train is here and another train is here. That's the only feasible situation. While in this piece of track between two stations, only one train at each time can pass. As you can see here, the timetable is feasible because the meet and pass is always at a station. Okay, the line always touch each other at a station, and the station are A, B, C, D, E, F. Okay, and the time is going from left to right. Now you can optimize this timetable. For example, you can improve the timetable introducing some robustness. One possibility to introduce robustness is introduce so-called recovery time in railway engineering. That is, I can design the timetable not necessarily with the maximum speed. So the speed curve cannot be really the one of the maximum speed, like the dotted one, but can be a so-called planned speed. I go at a reduced speed. All this time here is a recovery time. That means if I have a delay, I can speed up the train and recover. Okay, so I can introduce a number of times a planned speed that is higher than the maximum speed, and then can introduce some recovery time. Another form of robustness that I can introduce is so-called buffer time. Between two consecutive trains in the same resource, there might be a minimum safety headway distance between the two trains. This minimum headway can be enlarged, and if I enlarge this minimum headway, I start introducing a buffer time. So the difference between buffer time and recovery time is that the recovery time is looking just at an individual train, changing the speed of this train. The buffer time is looking at two consecutive trains on the same resource, that is the track between station E and D. This is another way of introducing robustness in the timetable. Now the point is that you can start playing with introducing robustness in different ways, but you will always end up at a certain point with the need of rescheduling trains, because you cannot foresee any possible disturbance and recover any possible disturbance through these techniques. So when you are in real time, you might have for example, a very long delay that might create problems to your timetable. Imagine that this train that should leave at this point in the timetable is now leaving at this point in time in the timetable. Okay, so there's a big delay in time. Let's try to see what will happen in the future after this delay. If I depict the train, the path is shift, and the shifting the path cause problems, cause conflicts. There is a conflict here between station C and D. There is a conflict here between station B and C. So the solution is no more feasible. Let's try to recover this, to solve this conflict by using the recovery time. So let's try to speed up the train. As you can see, the conflict is still here. The conflict is still here. You're just moving in time, the conflict, but the conflict is still in the same in time and space, but it's still in the same track. What changed really when you use the recovery time is the minimum possible delay, that is called the initial delay. If I speed up the train, the initial delay reduces. Here you see the initial delay reduces. If you see at the exit, without recovery time, the initial delay at the station A is this arrow. If you use the recovery time, the arrow is smaller. So the recovery time has surely an impact, reducing the delay of each individual train, but has no value in terms of solving conflicts. The conflicts are still there. And then in this case, you might use rescheduling. Okay. One possibility to reschedule train to solve such conflicts is to keep the timetable sequence. What do I mean with keep the timetable sequence? I do not alter the ordering between trains. I just shift the whole timetable of exactly this amount. So this is the amount of delay of this train in this station. All the timetable is shift. Of course, if I move the whole timetable, then the solution becomes feasible. But what is the consequence? The consequence is that you have a consecutive delay in multiple places at multiple stations for several trains. The the green arrows here are the consecutive delays. So now we understand what is a consecutive delay. It's a delay that is due to the propagation of delays, the propagation of the initial delays. Okay, and is also due to the rescheduling actions that we take. Actually, here the rescheduling action we take is shifting the whole timetable, so keeping the timetable sequence but shifting time. This is of course a rescheduling approach that in which reordering is fixed, ordering is fixed, routing is fixed. Just the timing is changed. And this is the solution. And you measure it as a number of green arrows. Let's see an alternative way to solve this problem. Let's use the first in, first out sequence. So the first train that is asking each resource will go first. So first in, first train arriving, first out, first train going out. Okay, first train asking for the resource, first train using the resource. Okay. As you can see, this is another possible solution to the rescheduling problem. And then you can see that the consecutive delays are different. There is a very big difference in these cases. Now the question is, what is the best approach? The timetable sequence, the first in, first out sequence, or another possible sequencing? Answering which is the best possible sequencing is finding the optimal solution to the rescheduling problem. Okay. Here, just to give you an idea of the importance of rescheduling, we took the whole country in the Netherlands, the Dutch railways, and we use as an input one delay, 16 minutes entrance delay. This delay starts spreading in the network if we keep the table sequence, and you can see the spread of delays here very easily because the white and yellow are small delays, the red and black, brown, black are the big delays. When you don't perform any reordering action, then there is a very big spread of delay. One delay causes a domino effect in the whole network. When you use an intelligent way, then we will see how, rescheduling, then you see you still have a spread of delay, but the delay is much smaller, okay, in the order of a few minutes. So here you see in one single slide the importance of rescheduling. Okay. Now we understand the importance of rescheduling. Now we'll focus on how to model and solve it. Oh, okay. Before going to the mathematical modeling, I give you some more information on the complexity of the train rescheduling problem. The train rescheduling problem so far is still largely solved manually. There are very few, okay, now no is too much, few advanced, this is old slide, few advanced tool exist to reschedule the train movements during operations. Well, what is the problem? Why the decision support, the automatic tools or semi-automatic tools are still few? One problem is the modeling precision. If you want to optimize the traffic flows, you need to very precisely model the dynamics of the movements of trains in the network and all the connected constraints. Also the robustness is important. Some tools are very useful and very well working, but only for very small disturbances. Only if there is one delayed train, few delayed trains. If you have multiple disturbances, then the system doesn't work anymore. It doesn't recover feasibility anymore. So this is very important to develop a robust tool that is able to recover many different types of disturbances. Another problem is quality. When I was discussing with the infrastructure managers in the Netherlands, they show me their tool to reschedule trains. Basically, their tool was a combination of local rules, like first in, first out rule that we discussed before, or other very simple rules. But it was very myopic because every time I was looking at a pair of trains in one special piece of track and taking decisions without having any knowledge of the consequences of these decisions on the other trains. So the point here is how do I ensure the quality of the solutions? The only way is through a global conflict detection and resolution. And this word global means that when you take an action, you need to see the consequences of this action. And the alternative graph formulation is a way to see that. When we will introduce a decision, for example, an alternative arc, we will generate a number of generate a new graph, and inside this new graph there will be a number of operations that will be involved in this change in the graph. Okay, so we will have to adjust the longest path in general to reach each node of the graph. And this is a global assessment of the decision. Then efficiency. Efficiency means not only finding a solution, not only finding a good solution, but also finding a good solution in a very tight, very limited computation time. That is typical from rescheduling purposes. So all these four factors create complexity in developing a tool that can be used in practice. And this is the reason why very few tools exist in practice, and most of them are working on very simple and sometimes isolated lines. Okay, now go a little bit more in deep on the modeling. To incorporate the UEC concept, we use the plug-in time theory. I don't want to spend too much time on that. I just show you that the plug-in time theory is a way to formulate the minimum headway time correctly and precisely between two consecutive trains that use the same piece of track. How do we incorporate the plug-in time theory? We have a block for each train. Can you see here? This is forming a block. So every time it's not just occupying one train. Just not look at the head of the train that is entering and the head of the train that is exiting, but we look at all the occupation of the train. So this block means that the occupation of the blue train in this piece of track. This train is occupying this piece of track. This other block means the red train that is occupying this piece of track. Okay, as you can see, these two blocks must not overlap, because an overlap between the blocks will means that the signaling system will switch from green to yellow or to red. So it's a kind of conflict to be solved. So all these blocks represent the routing of each train, so the blue and the red, and the blocks eventually touch at some stations, like here. So what I show you here is a feasible solution where the plug-in time theory ensures that the solution is feasible. Now, how do I represent this plug-in time theory and these traffic flows through the alternative graph? We use for each train a job. A job is a chain of nodes and arcs. Each node represents one train entering in one resource. So the blue train entering this resource here is this node. Then the arc means that the train is traveling, so the head of the train is moving from here to here, and here the head of the train is arriving to this new signal. This is another node, and so on. So through a chain of node and arcs, we represent the blue train moving in the network. So we need to give a weight to this arcs. These are so-called fixed arcs, and the weight depends on the travel time of the train in each piece of track. It is a block session between two signals. Then We have the same reasoning for the red train, so a chain of node and axe, and then we need to take the decision on the ordering. Now here we already know that the blue is first, then the red. So we will introduce this green axe that are the alternative axe, and we already know that the blue is before the red. So we introduce this arc going from here to here to represent that the blue is the first to use this common resource. Why we introduce the arc here? Because these nodes represent the operation in which the blue train is entering the next resource. And if we give a suitable weight to this arc, we can incorporate the minimum headway distance between the two trains, and then this allow the second train, the red train, to enter the next resource. Okay. In this way, we can simulate basically the traffic flows in the network. Now, what do we need more to simulate? We need to know at what time is expected the entrance time of each train, and we use these tags, and we use the fictitious node start node 0. These are release tags. And we also need to know for each operation, which is the start time of the operation. This is very simple because it's simply the longest path in the graph to reach the node. So if we want to know the operation related to this node, what is the start time, we just compute the longest path in the graph till this node, and we know automatically what time the simulation will start moving the red train, the head of the red train, in this point. So how can we not just simulate traffic flows, but also optimize traffic flows? To optimize traffic flows, we need to reintroduce the decision. Who goes first, the blue or the red? This is introduced by a pair of alternative axes. So you can see not just the green going from the blue to the red every time, but we introduce both, also the one going from the red to the green. So we introduce for each resource a pair of alternative axes. So we have 1, 2, 3, 4, 5 pairs because we have 1, 2, 3, 4, 5 resources. 1, 2, 3, 4, 5 resources. So this is actually the alternative graph of the problem. Actually, not complete. We need to introduce some more nodes and arcs. For example, if we want to model the departure time from one station, we might introduce additional release arcs to model the minimum departure time from the station. In this case, these nodes might be the departure time from a station. And then we might collect delays. For example, if we want to minimize delays, then we introduce this fictitious ending node n. We introduce so-called due date tags that are collecting delays in some special nodes of the graph. And we basically, through this node, collect the delays. Okay. So the result is that we have that we need to select for each alternative pair one arc. And if the selection does not contain any positive left cycle, then is a feasible selection. That means is a feasible simulation of the traffic flow in the network. This is a feasible traffic flow simulation because there are no positive left cycle in the graph. In this case, the red train goes first in each resource. It's the opposite solution compared to the previous solution I showed you. So in general, from a mathematical point of view, on this graph, we are searching for a complete selection. That means for each pair of alternative arcs, I select exactly one arc in such a way that I minimize the longest path from the starting node to the ending node. So from the node 0 to the node n, we want to minimize the longest path in this graph. Okay. So if we find a solution to this problem, minimum longest path in the graph, we have solved at the same time the train scheduling problem in which we want to minimize the maximum consecutive delays. So this is an example of application of the alternative graph to a train scheduling, to solve a train scheduling problem. I just recall here that we have a set of nodes, set of fixed arcs, and a set of alternative arcs. Alternative arcs are the green one, the fixed arcs are the black, blue, and the red arcs, and the nodes are all the nodes that you see. Now the question is, can I move from an alternative graph representation of the problem to a linear program, to be more precise, a mixed integer linear program that I can give to a commercial solver to solve the problem? Yes, it's very simple. As I told you before, in the alternative graph, each node is an operation. And in the alternative graph, each arc is a constraint. Then if we want to model the problem as a linear program, it's very simple. We just need to give a name, an identifier to each node, so to each operation, and more precisely to the start time of each operation. So the variable related to each operation, the timing variable. And then we give a name to each arc in the graph. So this is exactly what I'm doing now. I'm giving a name to each node. This is node 1. And the timing variable of node 1 is t1. This is node 9. The timing variable is t9. This is node t, final node. The start time is tt, okay, and so on. Or simply the start time of the final node, I call it t. This is the initial node. The initial node is a given information. T0 is usually the time in which I start the simulation. And then I give a name to each arc. The name of each arc is given simply looking at the start and end nodes of each arc. So this arc is moving from 0 to 1, so it's W01. And with W01 is, 01 is the name of the arc. W01 is the weight of the arc. Okay, so once I introduce all this terminology, it's very simple to write the linear program. Let's look at it together. Okay, allora, okay. Objective function is not so important. What we know is that the objective function is depending on the timing variables, t, and the ordering variables, the alternative arcs. Let's call them x. Then we will see how to formulate those. So it's objective function depending on these two types of variables. Then let's write the constraints. We remember each arc is a constraint. So I want to introduce the constraint related to this arc. If t0 is a well-known information, no? Okay, the start time of our simulation is time 0 by convention. Then t1 is exactly equal or larger than w01. This is exactly the constraint that is related to this special arc. Let's take another constraint, for example, this one, t12. Sorry, okay, t12 must be larger than t11 plus w1112. Let's look at w1112. Is this arc here? So this constraint is related to this arc. T12 must be equal or larger than T11 plus the weight of this arc. So as you can see, every time you point to an arc, you have a constraint. Okay. How do I model the alternative arcs? These are very special arcs. Okay, these are all the dotted green arcs. Are special because I don't want to introduce both in the graph. I just want to introduce one of the two. So I need to introduce a sequencing variable that is basically a binary variable. If I look at these two arcs, they form a pair of alternative arcs that I use to model as a circle to chain the two arcs. I just want that one of the two is in my solution. To do this, I first need to formulate each individual arc, and then I need to introduce a variable to connect the two arcs. Okay, here you see exactly this formulation. Okay, if I just look at the first part of the two constraints. Okay, so just look at this yellow part here. If I use the yellow part, it's very simple to understand. This arc here means that T1 must be equal or larger than T8. T8 plus W81, and exactly this constraint. The other constraint is T7 must be equal or larger than T2 plus the weight of W27. Okay. So I introduce these two arcs. Now I need to introduce the fact that only one of the two can be my solution. To do this, I use X variable, and I use the big M trick. So I put minus M, and one time I put 1 minus X, and the X is the variable related to these two alternative arcs, 8, 1, 2, 7. And then in the other constraint I write minus M multiplied by X, 8, 1, 2, 7. Now, if X is equal to 1, what happens? That here, this minus M disappear because 1 minus 1 is 0. And the minus M multiplied by 0 disappear. And that why in the other minus M remain. So if I have T7 equal or larger than something minus M, and minus M is a very big number, then I'm writing that T7 is equal or larger than minus very big number. So it's always valid. So there is no constraint on T7. So basically what I'm doing here, putting X equal to 1, is canceling the second constraint. Canceling this constraint means that I cancel the arc going from T2 from the 2 to 7. This means that the other constraint is still there, and the other constraint is still there, and the minus M disappear because 1 minus 1 disappear. So at the end, what I have with fixing the X variable, I have that I introduce this arc. So I introduce this arc when this X variable is equal to 1. In the same way, I can reasoning with the other X variables, and I can insert these other arcs. At the end, I will have one arc for each pair, and then I will have a start time for each operation, and I will have a final solution to my problem. Now, how do I alternatively can optimize my problem? I don't want to use the MILP, because when you increase the number of variables, and especially when you increase the number of sequencing variable, the number of big M values might be more and more. And every time you have a big M value for a commercial solver is a very big problem to handle because it's very difficult to generate cuts with a big M value. So commercial solver is less and less good when you use so many big M values. So let's try an alternative approach. And this alternative approach is a dedicated software. Now, we don't have much time to talk about the algorithms in this software, that is AG library, but I will try to give you an idea on how the AG library works. And then I give you some experiments to compare the two approaches and some conclusions. Okay, the idea that we have here, the approach that we decide to use is first we solve the train scheduling problem, which we fix a route for each train. If we find a feasible schedule, then we ask ourselves, can we change the routing on some trains to improve the solution? Okay. Are there any routing alternatives to improve my solution? And then we solve a so-called train rerouting problem. And we iterate as soon as possible, solving these two subproblems. So, as you see, the decomposition that we propose is grouping two different classes of variables. In the train scheduling problem, timing and ordering variables. In the train routing problem, only the routing variables. With this decomposition, we develop several algorithms, both heuristics and exact method, a branch and bound algorithm for the scheduling problem. And for the routing problem, we develop a local search first, and then we improve the local search to tabu search, variable neighbor search, hybridization of variable neighbor search and tabu search, and so on. So we opt for method heuristics in this case, and we opt for heuristics and exact method in this other case. Let's see now an industrial project in which we used the AG library. Okay, this project was, as I told you before, with Alstom company, and they had their own decision support tool to optimize traffic flows. But the local solver, the local conflict detection resolution was quite weak. When the disturbances were increasing, and this was also the case that was most needed, the software, the local decision support was not working, was not finding any feasible solution. So they said, okay, let's try to replace the local solver with AG library, that is more global solver. So we create these two links going from left to right and to right to left. This took some months to do that. We implemented the links, so we incorporated the AG library into their software. And then we introduce a new formal intelligence. As a result, the AG library was systematically better than the local solver to recover disturbances. For this reason, we need not. I do not show you the comparison with their local solver, but I show you the comparison with a commercial solver. And the comparison is done for a UK network nearby the city of London. And this is the level of complexity in the infrastructure representation, so the level of block session and track circuits. And this is the type of disruption that we were dealing with. Some piece of track between two stations was still available for traffic, but at lower speed. As a consequence, a solution was either moving trains very slowly or moving trains after the disruption. Okay, here you see some yellow stars that are the conflicts. Here you see the solution in which the conflicts almost disappear. What here was interesting is that you need to decide either moving trains slowly in the disrupted area or postponing trains. And this is the overall network, is the piece of the East Coast Main Line with more than 800 trains per day, 90 trains in our peak hour traffic flow optimization, 35 stations. Here you see the platforming and traffic flows representation of a time-space diagram. We were doing the comparison with the local solver, but we were always better. With the commercial solver, also we did a comparison, and we used the commercial solver basically as a benchmark. We gave the commercial solver 1 hour to solve the problems. There were 29 instances on a normal, quite low performing computer. And then we ask the Cplex IBM iLog solver to solve the MILP with 1 hour time, and we ask the AG library to solve the same problem with up to 20 seconds, because the real-time constraints was 20 seconds. And we found that the commercial solver was failing 6 times. We never failed to compute a solution. The commercial solver was going slightly better, only 1 time better than us in computing one more optimal solution. But the commercial solver was in average asking more than 1,000 seconds to find a solution, while we were asking on average much less than 20 seconds, 11 seconds on average. Actually, later results in which we replace the Tabu search with a more advanced variable neighborhood Tabu search was improving this performance to 22 optimum. Okay, so I show you not the best performance actually of the solver, but it's interesting to see that when you compare, even if you group the instances in small, medium, and large size, depending on the number of operations that are involved in each optimization, you see that when you increase the instances to large size, the Cplex solver often fails. Doesn't find any feasible solution in 1 hour computation time, while our solver is always able to find a feasible solution. If you look at the computation time, time to compute better, time to compute the best solution, we are almost flat, always very, very constant. While the commercial solver fails, okay, but also when does not fail, sometimes it takes a lot of time to find the best solution, a time that is very far from the practical application. This is a demo that we did together with Alstom Ferroviaria. Here you need to see that one of the computers here is basically the AG library that is connected to their traffic management system. And here the people that you see are a mix of developers, dispatchers, and some railway managers. They were looking at what happens when they click use AG library and solve conflicts. Here is a list of publications for further reading, and my last slide is about a special section that we are organizing at IFOM's annual meeting 2021. You can also follow remotely the meeting. It's nice and strongly connected with this talk, because in this section we will have the latest developments of job shop scheduling for solving railway traffic management problems. I invited to this section prominent researchers in this field, and also researchers that have a well-established track of publications. And I asked them to show some current research directions. And there will be a professor for Foods University showing how to transform the train scheduling problem into a parallel machine job shop scheduling problem with bottling constraints. Then Marcella Samar from our research group will discuss effective pruning rules that are speed up strategies to deal with the best way to solve special constraints in this problem. Then there will be Carlo Mannino, that is a well-known person in this field, that will show one of his real-life applications in Norway. And then there will be a professor from Virginia Gentile University that is dealing with a very special problem that is a combination of metro traffic flow optimization and commuter traffic flow optimization, how to combine these two traffic flow optimization through the job shop scheduling problem. And the last speaker is Professor Comet, that will talk about how to introduce stochasticity into the alternative graph formulation to better manage traffic flows. Okay, thank you very much for the attention.